Hello, I'm Daniel Amigo, and I'm pleased to present the paper entitled Segmentation Optimization in Trajectory-Based Classification. As this year we will not see each other in person, before I start, I want to show the details of the members of this research and our artificial intelligence group in the University Carlos III of Madrid. Nowadays, the analysis of monitoring information can generate useful context information to solve existing problems. An real problem in the maritime field is the level of risk in certain areas of the world, such as the Gulf of Guinea and the Middle East and Asia, where more than 10 cargoes every quarter are hijacked by pirates. There are technologies such as automatic identification system, which increases the maritime domain awareness by communicating collaboratively all ships its position, monitored as well by base station and satellites. However, it still has flaws, as the pirates can simply turn off the transmitter and not be detected. Focusing in real problems like this one, we started this research aiming to create useful information about the maritime context, using only the movement of the ship, its dynamic. This information is generated through a supervised classification of the ship type, but it will be easily used in other types of vehicle. This process is carried out by an automated system developed in previous works and formed by multiple components. In previous works, good results have been achieved by identifying whether the ship is fishery or if it is not, although some components can be improved. In this paper, we will check the impact of the trajectory segmentation component. In previous works, good results have been achieved, identifying whether the ship is fishery or if it is not, although some components can be improved. In this paper, we will check the impact of the trajectory segmentation component. Therefore, this research aims to explore the trajectory segmentation techniques in the literature in order to understand their strengths and drawbacks depending on the problem to be solved, to analyze the impact of those segmentation algorithms within the classification problem, and to obtain a deeper knowledge of the maritime context to be able to produce useful information. After that, we will like to introduce the system developed in previous work in order to explain its functionalities, in particular to show the problems of the current segmentation component. First, the data source is an AIS data collected and offered by the Danish Maritime Authority. It is composed by a daily batch of reports detected by several base stations in the coast of Denmark. Every ACE contact provides this information: static information that identifies the vessel, dynamic information of the movement of the vessel, and the route info. We only use the MMSI identifier, the ship type for the classification, and the time and the geographic position. Therefore, the first real component is the data cleaning, processing the raw data to obtain a clean track that fulfill our minimal quality requirements. Using this vessel as an example, we can see that all its measures are divided applying time restrictions, eliminating large time jumps and extreme outliers. Then, on its valid trajectory, we take a zoom into the valid trajectories. We have 19 valid trajectories, and if we take one of them, for this example, a second cleaning is applied to eliminate clearly erroneous reports like these two caused by system malfunction, so that the cleanest possible trajectory is introduced to the system. The next process is the track filtering. The cleaning has provided the most suitable reports, but these do not show the real dynamic of the vessel. To obtain it, an estimation filter is applied, in this case an interactive multiple models, to obtain a smoother and more realistic trajectory, eliminating the intrinsic noise associated to the reports, and in addition performing the change of geographic coordinates to Cartesian coordinates. The next step is the track segmentation. In order to properly classify the trajectories, it is necessary that they are comparable. Since the trajectories have different duration and lengths, in the previous paper we decided to divide the trajectories into comparable sub-trajectories, each one with 50 measures. In this example, we have a clear view of the problems of this decision because the last points are discarded, and also each segment could be formed by different types of movements. As we can see here, segment 1 is formed by curves and straight lines, which will not help the classifier. The next step is the feature extracting. Using the dynamic of each segment, it extracts different dynamic values like course, distance, speed variation, etc. All these features are also summary in statistics, generating a vector of inputs of each ship into the classifier. Later, this vector is introduced on each classification. We use two classifications different and support vector machines that generates a hyperplane to separate the vessels that are fishing than the ones that are not fishing, and with a decision tree that applies different numerical limits for the input values. Once the whole process is introduced, this paper explores more informed and appropriate segmentation solutions. Each solution has different objectives and therefore calculated in different ways, trying, for example, to preserve the position of the ship, its speed, its course. Most of these algorithms are adjusted by thresholds, so it's important to adjust them to the dynamic on which will they act, because as finally shown here, each algorithm produces different segments, even in a simple example like this. A total of 7 different segmentation algorithms are implemented, and by using several parameters to adjust them to the problem, 32 variations are tested. Moreover, since the classification is about fishing and not fishing, in previous work we analyzed the imbalanced problem of the fishing type class, and we will test it here also. So 3 variations are also tested. Finally, as we commented before, each experiment is applied to both classifiers, generating a total of 192 experiments. Once all the experiments are completed, to check out how well they have classified, we show the accuracy of the overall problem, classification problem, and the F-measure metric, which shows the success of the minority class, in this case the fishing class. If we compare these results with the original segmentation, we can see that they are slightly better results in both variables, showing that a most appropriate segmentation has helped the classifier. Even so, it's clear that the problem of the classification generates a multi-target problem. Then a Pareto front is observed, where there is no global solution better than the others, but the best solution must perform an optimal balance between both metrics. Finally, as we just have seen, there are segmentation algorithms that are better classifying, standing out the squeeze algorithm. Even so, this is a multi-objective problem, so there is no optimal solution, there is a Pareto front. Finally, the SVM usually has better results in both metrics, but there are times that it collapses and classifies everything as not fishing. In future works, we have shown that this approach has potential, but needs to be improved also. Other classification algorithms could perform better, and trying to apply this system in other fields like aviation that have more different maneuvers maybe is a better field for this problem. Finally, a review of the literature of the segmentation algorithms is necessary, as all the research is poorly collected, which makes it difficult to know the current status of this field. Thank you very much for your attention. For more details, I refer you to this paper as well as the previous one. Do not hesitate to contact us by email for anything. Thank you.